Okay, folks, it gives me great pleasure to welcome Stuart Gomani to speak with us today. Stuart is no stranger to us, although he's unfamiliar to us because poor man got forcibly repatriated during COVID and then ran out of study leave. So it's been a bit of a torturous task, but hopefully we'll be seeing him again next year. Stuart is employed at the Malawi University of Business and Technology and has been doing a PhD with myself and mostly with Professor Rodrigues. And he will speak to us today on the dance codes and graph invariant under two macro groups, M11 and M12. Over to you, Stuart. Thank you.
Thank you so much. Let me start by expressing my sincere gratitude to everyone for making yourselves available to this presentation. So in this seminar, we are going to discuss designs, codes, and graphs that are preserved by two Mathieu groups, M11 and M12. So what we're going to do first is we're going to go through terms, the definition of terms that will be pertinent to this presentation. Then we are going to share the technique that we have used to construct our designs in the talk, and it is called method 2. Lastly, we are going to discuss the results that we have been able to obtain under this construction. So the action of a group, which we are going to be denoting by G, on a set omega, is called transitive if and only if given any two elements of the set omega, you can find a permutation in the group that maps one element to the other. And the permutation group G acting on a set omega is said to act primitively if that action does not lead to any non-trivial partitions of the set. So a set which we can denote by n capital of elements of the group conjugate with each other is called the conjugacy class of the group containing that element of specific order n. Now, let G be a finite group acting on a set omega. Then the map, which we denote by pi sub omega from the group to the set of natural numbers, which maps a permutation of the group to the number of elements that are fixed by that permutation, is called the permutation character of the action of the group on omega. And we are going to be denoting that character by high sub ti of x. And the setup is that omega is the set of conjugates of the maximal subgroup that we're working with. And we are denoting these maximal subgroups by ti. Now, let calligraphic date be an incidence structure. And by that, we mean D should be a triple of a point set, a block set, and an incident set I. This incident set should be such that it is sitting inside the Cartesian product of the point set and the block set. Now, if the ordered pair involving an element of the point set for D, which we are denoting by P, and a block B, which is an element of calligraphic B, if this ordered pair is an element of the incident set I, then we say that P is incident with the block B. So for a positive integer T, we say that D is a T design if every block is incident with exactly k points. By that, we mean that this block contains exactly k points. And every T distinct points that we can get from the point set are together incident with lambda blocks. So once we have got that setup, we are going to write calligraphic D to be a T VK lambda design, where VK and lambda are parameters of our design, and V is the number of elements in the point set of the design. So once we have got such a design, the design calligraphic D is going to be called symmetric if it has the same number of points and blocks. In other words, if the size of calligraphic P and the size of calligraphic B are the same, that design is called symmetric. If gamma is a finite graph with adjacency matrix A, then the O1 vector is an eigenvector with eigenvalue kappa under the necessary and sufficient condition that this graph is regular and it has got valence kappa. So if the graph is regular of valence kappa, then the multiplicity of the eigenvalue is the number of connected components of the graph. Now the graph that is called strongly regular of type n kappa lambda mu is a regular graph on n vertices with valence kappa, and it is such that adjacent vertices of this graph are together adjacent to lambda vertices, and any two non-adjacent vertices are together adjacent to mu vertices. So we're going to see the connection between codes that are preserved by the designs that are preserved by M11 and M12, how those codes are connected to strongly regular graphs. Particularly, we are going to look at the codes under M12 connected to a strongly regular graph with these parameters. So what we have done first is to determine all 1 VK lambda designs, which we are denoting by calligraphic B. And these designs have been constructed for maximal subgroups and conjugacy classes of elements of the Mathieu groups M11 and M12. Now, with this, what we are looking for is to make sure that M11 and M12 are preserving the designs that we construct. And the way that they'll be preserving is that they'll be acting primitively on the blocks and transitively on the points of the design. That's why we just call these designs block primitive and point transitive designs. After that, we're going to determine automorphism group for each corresponding design. And from the instance matrix of each design, we're going to construct binary codes, which really are binary row span of the instance matrices of the designs. And lastly, we're going to show graphs that we have managed to construct from the designs under the construction technique that we are going to share next. So the construction technique is called, and it is according to Mori and Key, and it is such that if you let G be a finite simple group, you select a maximal subgroup from that group, and you select also a conjugacy class of elements of some order in the group. And the selection should be such that the intersection of the maximal subgroup and the conjugacy class should have at least an element. Again, what we want is to let high sub T be the permutation character afforded by the action of the group on omega. Then the intersection of the maximal subgroup and the conjugacy class is what we're going to be calling a block. And what we need is to set up a set that is containing this initial block plus the block. And to determine the conjugacy of that block, we're going to allow the group that is acting at that time to act on that initial block by conjugation. So the calligraphic B is going to be a set containing the block plus all the conjugates of that block. So once we have got that setup done, then we are going to say we have got a 1 VK lambda design, where the parameter V is just the number of elements in the conjugacy class of elements of a particular order. The parameter K is the number of elements in a block of a design. And high sub T of X is the parameter lambda, which really is the permutation character afforded by the action of the group on omega. So once we have that, then the group that is acting is actually an automorphism group of the design. In other words, the group preserves the design. So it is going to preserve, like we said before, by acting primitively on the blocks and transitively on the points of the design. Now, once we have a design under this construction, method 2 construction, the parameters of this design are related to the index of the maximal subgroup in the group by this relation. So this is a relationship that is taking the parameters of the design to the index of the maximal subgroup, lambda V over K. Now, because the maximal subgroups are self-normalizing, By that, we mean that the normalizer of the maximal subgroup is just the maximal subgroup itself. So because of that, then we see that the action of the group on the right causes of the maximal subgroup by right multiplication is equivalent to the actions of the group on the conjugates of the maximal subgroup by conjugation. And the consequence of that equivalence is that the maximal subgroup in the group is just equal to the number of blocks of our design. But also, we see that the index of the maximal subgroup of the group is equal to the number of conjugates of the maximal subgroup in the group. Now, our designs are constructed from maximal subgroups and conjugacy classes of elements of the groups under discussion. So we present here the information about the maximal subgroups and the conjugacy classes as they appear in the Atlas of Finite Simple Groups. And these are the conjugacy classes and maximal subgroups and M11. And the maximal subgroups and conjugacy classes under M12, again, we obtain this information from the Atlas. Now, in a one VK lambda design, the first parameter of the design V is given. We can obtain that from the table of conjugacy classes of elements. The moment we allow the group to act on omega, the action used for us the parameter lambda, which is the high sub T of X, the permutation character afforded by that action. Now, because we can obtain the index of the maximal subgroup in the group by using some techniques in group theory, or indeed, we can make reference to the table of the maximal subgroups of the group that is in the Atlas. So we can just refer to the Atlas to find the indices of the maximal subgroups. Then, having known these three variables, we can calculate the last parameter of the design here using Fisher's result that we just shared prior. So the designs that we construct using this technique are not symmetric in general. Some are, but in general, they are not symmetric. Matter of fact, all the designs that we have constructed, both for M11 and M12, they are 77, but out of the 77, only 4 are symmetric. So if we focus on M11 and we select the maximal subgroup from M11 and we fix an element of M11 of a particular order, which is non-trivial, then the parameters of all non-trivial designs under M11 are as given in this table here, where the second column in the table is giving us our notation for the maximal subgroups. The third column is giving us the order of the elements as they exist in the conjugacy class. So we can as well look at this column as representing conjugacy classes of elements of the orders that are here. Order 3, order 2, order 3, and so on. The columns, the next 3 columns are giving us the parameters of the designs that we have managed to construct using this construction method 2. And the last but 1 column is giving us the indices of the maximal subgroups in the group. And we have denoted these indices by B. We're going from this point forward, we're going to be using B for the index of the maximal subgroup in the group. What we're showing in the last column here are the full automorphism groups of the designs that we have constructed. Remember that we have just said the groups that are acting are actually automorphism groups for the designs. Not the full automorphisms. What we're presenting here is the full automorphism of the design. In other words, we at M11 and M12 as subgroups of the groups that we have shown here. Matter of fact, because our groups are simple, we can actually define an embedding map of the groups into these automorphism groups. Now, when we switch focus to M12 and we have the whole structure of a design under M12, then up to isomorphism, there are 52 one designs that we can construct under method 2. And those designs are presented in this table. So the information is similar to the information that I've shown under M11, where the third column here is giving us the conjugacy class. So here we are representing the conjugacy class by a letter B, and the number in front of this letter is giving us the order of the elements in that conjugacy class. And again, the last column is giving us the full automorphism group for each design that we have constructed. There are 52 of them in total, up to isomorphism, of course. So I think we need to explain a little bit how we get the full automorphisms of these designs. And we use the technique that is according to Mori and Tungle. We fix a point set X of VK lambda design. And we select lambda blocks from that design. And we select those lambda blocks containing the point that we have fixed. And so now we define an intersection of those lambda blocks, and we denote that intersection by I sub x. So what we're going to do is we're going to take the number of elements in the intersection and divide that number into the into the size of the point set of the design and the size of the block. So once we have done that division, we end up with another structure, which is below here on the slide. But it is another structure that has got the first parameter and the second parameter reduced by this division. And you know, amazingly, this structure is also a design. It satisfies the structure of a design. And we call that a reduced design, denoted by calligraphic D sub I. This reduced design and the intersection of lambda blocks have become absolutely critical in us determining the automorphism group of the designs that we have, as we are showing in this next slide. So the general structure of the automorphism groups for the designs under M11, like the automorphism groups of these designs are isomorphic to one of these groups. So you notice SIM11 and M11 are two groups that are automorphisms for designs constructed from conjugacy classes of involutions. So these are elements of order 2. So typically, if the conjugacy class is a class of elements of order 2, then the automorphism group of their designs are isomorphic to one of these. The moment the conjugacy class is a conjugacy class of elements of order greater than 2, now the automorphism groups are isomorphic to groups of this structure. Symmetric group. Now, if you look at the first group, for example, this is a symmetric group on a set of size, number of elements in the intersection of lambda blocks. Power, number of elements in the point set of the reduced design. So that's a non-split extension of that group with a symmetric group on the P points. So you can see there that the intersection of lambda blocks and the number of elements in the point set of the reduced design have become absolutely very important in us determining the automorphism groups of these designs. Similarly, if the design is an M12 invariant design, then the automorphism group of such design is isomorphic to one of these groups. And again, symmetric group on 12 points, massive group on 12 points, and the extension of M12 with a subgroup of order 2 are the typical groups that are automorphisms of designs constructed from conjugacy classes of elements of order 2. For the conjugacy classes of elements of order greater than 2, again, the intersection of lambda blocks and the size of the point set of the reduced design becomes absolutely critical in determining the automorphisms. Automorphism groups of the designs for lambda values that are at least 2 in both cases. Now, if lambda is equal to 1, if you've got a design where lambda is equal to 1, then the design, the structure of the automorphism group of that design is actually just a width product of the symmetric group on K points with a symmetric group on B points. So this product turns out to be just the non-split extension of the symmetric group on K points with a symmetric group on B points. So always that's the structure of the automorphism group for lambda equal to 1. For lambda greater than or equal to 2, then those are the variations that appear for the automorphism group of the designs. Now, from the instance matrices of the designs that we have, we can construct binary codes from them. And these binary codes are simply the space that is spanned by the incidence vectors of the blocks over some finite fields. And because these are binary codes, then the finite field is a field of size 2. It is a set of 2 elements. So normally, the automorphism group of a code sits inside the automorphism group of a design in general. But now, because the designs that we have constructed under this method are such that the minimum distance of the code, sorry about that, the minimum distance of the code that we have constructed is just equal to the number of elements of a block of the design. And if the vectors, if the vector is in the block, then that vector is just a codeword of minimum weight. In other words, the codes that we have constructed are spanned by the minimum weight coordinates. And because of that, we see that the automorphism group of the design relates with the automorphism group of the code with equality. So now we present all the binary codes over a finite field of 2 elements that I've managed to construct from the corresponding designs constructed from M11. And as you can observe in the 4th column, these are the same automorphism groups that we showed for the designs. Now, when we come to M12, we could only construct 8 binary codes from their corresponding designs. Computationally, it became a big challenge to be able to obtain the other codes from the designs. So we could only manage 8. But the reason why we have found it necessary to show them in this talk is that if you can focus on the first code, the 11-dimensional code of minimum distance 165, we have managed to construct what is called the how of that code. And the how of that code is the intersection of the code with its dual, the C pair. So we take that code, you intersect it with its dual, and what we obtain is a 10-dimensional code of minimum distance 240. So clearly, this is a code that has got much better error correction capabilities than the original code. That's not where the story ends. What is actually very interesting about this code is that the non-zero vectors of the code, the weights of the non-zero vectors of the code, take only 2 values. So 528 vectors are of weight 240, which is the minimum weight, and 495 vectors are of weight 256. So only 2 weights, 2 numbers for the weights of the non-zero vectors of the code. And such a code is referred to as a 2-weight code. Now, what is interesting about a 2-weight code is that if you put a 2-weight code, and this is the weight enumerator of that code, was in that code are related to a strongly regular graph using these relationships. So V is the number of vertices for the graph, and it is equal to the number of vectors of the code, of the 2-weight code, which is the variance of the graph is related to these variables of our code, where Q is the number of elements in the finite field where this code is defined. And so on. So the other parameter mu for the strongly regular graph is related to these weights and Q values of the code. So because there's a relationship between the 2-weight codes and strongly regular graph, we see that for the 2-weight code that we have managed to construct by taking the how of this code, we have managed to construct this strongly regular graph of these parameters. And it is a strongly regular graph with eigenvalues 15 and minus 17, with respective multiplicities 528 and 495. This is the point that motivated us to think of doing something more to the structures that we're developing from M11 and M12. And the first thing that we decided to do was to refer to literature. If you have got a design under the method 2 construction, you can actually define a graph from that design. And if you are to define that graph, automorphism of the graph is equal to the automorphism of the design. And literature fell short of showing us exactly the graph. It's just stating that you can construct a graph without showing us exactly how that graph would look like. And we felt like we should fill that gap by defining that graph that will have those relationships. And the first graph that we managed to construct was a graph based on a VK lambda design where lambda values are at least 2. So from that design, we construct a graph GAM of vertex set V and edge set E in such a way that the vertex set of the graph is just equal to the block set of the design. And adjacency in the graph is defined by taking the intersection of lambda blocks and making sure that the intersection of lambda blocks has at least an element. And with that, we're able to obtain a graph of order, the index of the maximal subgroup in the group. By order, we mean the number of vertices that this graph has. And the graph has got size V over number of elements in I beta. By size there, we mean the number of edges of this graph. Now, one thing that you can notice is that the number of edges this graph has is equal to the number of, is equal to the size of the point set of the reduced design. So that striking coincidence was, we found that striking coincidence quite interesting when we first defined this graph. But when we found we can try and define another graph. And we constructed another graph based on a one design where lambda is at least 3. And we construct a regular graph from that design in such a way that the vertex set is again the block set of the design, but now our adjacency is defined differently. First, we fix a vertex E sub j, and we take an intersection of lambda vertices that are including bj that we have fixed. And that intersection defines lambda minus 1 edges, bj b1, bj b2, up to bj lambda minus 1. So we have created lambda minus 1 edges out of this intersection. So we find that with that, we're able to have a graph. And that graph, again, has the size of the vertex set equal to index of the maximal subgroup in the group. Of course, this is obvious because of our choice of A. And the number of edges in that graph is given by this expression, lambda squared minus lambda times V over 2 times size of I sub alpha. Always, we made sure that the relationships that we are developing are defined by the parameters of our design so that we know if we have the design, we can come up with a graph using the parameters of the design. And of course, it suffices to say that we were using the Fisher's result to make sure that this is the case, that we are able to relate the parameters in the graph to the parameters of the design. There was a third graph that we managed to construct. This third graph, again, was defined on a one design, but this time with the lambda values at least 2. And we managed to construct a regular graph from there in such a way that the vertex set of the graph is equal to the point set of the design. And adjacency is defined if given any 2 vertices from the vertex set, which we denote by beta and alpha, is going to be adjacent to alpha if beta is in the intersection of lambda blocks. And alpha is in the union of the lambda blocks excluding the intersection. That's how we defined our adjacency there. So if we define adjacency in that way, then we see that we obtain a graph of vertex set equal to V, clearly from the way we have defined the vertex set of the graph, equal to the point set of the design. And the number of vertices of that graph is given by this expression there. Lambda squared V times K minus 5 of I sub beta over 2. And again, another thing we can share is that the degree of this graph, which is the valency of the graph or the number of neighbors of an arbitrary vertex in the graph, is given by this expression. Lambda times k minus number of elements in I sub beta. So a few things that we notice is that from graph 3, the graphs, the designs that we obtain, the designs that we have that should give us graph 3 should be such that at least one of these parameters, lambda, v, and k minus number of elements in lambda blocks should be even. At least one of them should be even, so that the number of edges in that graph should at least be a natural number. And if from that design, if the design has lambda equal to 1, then the graph 3 changes to a disconnected graph. It's no longer the graph that we have shown. It's a disconnected graph. Because if you have been following graph 3 the way we have constructed it, if you pick any two vertices that are in different blocks, then those two vertices would not be adjacent. So obviously that changes the degree of an arbitrary vertex. The degree will become k minus 1, and so on. Because at the fact that it's disconnected, it means we are losing edges at each successive vertex. So the parameters of this disconnected graph come different from graph 3. However, if lambda is greater than 1, then graph 3 is actually a connected graph. Obviously, because if you have got a vertex which is in the intersection of lambda blocks, then other vertex that is in the union of those lambda blocks, when you exclude the intersection, becomes adjacent to that bed. So it is a connected graph. The last striking thing that we can notice is that the parameters of the reduced design, which we denote by calligraphic B sub m, can be deduced directly from the results of the graph 1 that we constructed. We found that relationship, that interplay between the design and this graph quite interesting. So what we have seen from the action of M11 and M12 on some set omega, and the set we choose to be the set of conjugates of the maximal subgroup of the group, is that this action has revealed structures that have got very interesting algebraic and combinatorial characteristics, which we are convinced that, which we have demonstrated, again, the natural connections between designs, codes, and graphs. And we are convinced that these relationships that are coming from the structure of M11 and M12 would give us a platform to do many more further investigations in the future, particularly in the study of hierarchical codes and graphs. And for the first time in the study of one designs under method 2 construction, we have defined irregular graphs based on the one designs, in which the size of the intersection of the lambda blocks in that design have become absolutely important, very important in the constructions. This is the end of the presentation. Thanks.
Thank you, Stuart, and impeccable timekeeping, sir. Are there any questions from this audience? You can look online. Looks like we're letting you off easy here, but no.
I have a question.
Go ahead, Bernardo. Come on.
Okay. I think Dan's also has a question. I saw Dan's raising his hand.
Yeah, no, but you're online, so just go ahead. It will be easier.
Okay. All right. Thank you, Stuart. Thank you for the talk. I think you've been very exhaustive and comprehensive in a way. You've given good explanations of the problematic at hand, and you've also been able to exploit a lot of the structure of the group and the connections with the structures that you've revealed to be invariant under the group. There's just two remarks that I'd like to make. One is with regards to the description that you've given for the automorphism groups, particularly when you referred to the automorphism group of the designs coming from M11 and M12, exactly this slide. The remark is simply to let you be aware that these are not non-split extensions. They are, in fact, split extensions.
Oh,
They are not
okay.
non-split,
Yeah.
they are split, because it's a semi-direct product of the corresponding symmetric groups. And the other is with regards to whenever you construct an incident structure, in the case you had a design and you took a row span over a field of your choice, in this particular case, field of 2 elements, the codes associated to that, the inclusion that you provided is in fact reverse. Remember that the automorphism or the code that you're constructing is derived from the row span of the incidence matrix of the design. So the rows of your design or the incidence matrix become generators for the code. So then the automorphism group of the design should sit in the automorphism of the code, not the other way around.
Oh, okay.
Yes, it's the automorphism of the design is included in the automorphism of the code. And in some instances, this can be the same. And this is what you've shown, that in some instances, this should be the same. But one thing I think that needs to also be mentioned is, why is that the case? Why is it the case that in some instances, an equality can be attained?
Okay.
Yeah, I think if you can comment on that, that would be good.
Yeah, I think I gave the explanation that the minimum distance of the code is the size of the block. And if the vectors in the block, I mean, if you have got vectors that are elements of the block, then the vectors are actually codewords of minimum weight.
Is that true in general, or is that specifically true in this case?
That's the observation we made, at least for these ones. Maybe in general, we need to exploit more.
Okay. All right. Okay. Okay, Garrett, thank you. I think I'm satisfied.
Thank you, Bernardo. Thanks.
Mine is a simple question. It's to do with choosing to work with the Mathieu groups. What motivates you to look at those finite groups over and above other finite groups that are there? Is there something special about these two groups in terms of the structure?
Well, actually, it's the lack of information about the structure that was motivating. When we read literature, there's information about M11 and M12, the information about the Mathieu groups, but the information is a bit scant, at least from my experience. The information is not so much. And the desire to get to know more about the structure of the Mathieu groups is what made us to study these Mathieu groups more. And there's no better way to understand the structure of a group than allowing it to act on some sets and see how that happens. But then again, what led us to the Mathieu groups in the sporadic class is the fact that the desire has always been to work with simple groups. Because we know that simple groups can be embedded into the automorphism group of a structure that they act on. So for us to have a deeper understanding of a group, we want that group to act on something and preserve that thing. So simple groups are quite nice in making sure that we achieve that. So if our desire is to work with simple groups, then that takes us to the classification of finite simple groups. And in the classification, we see that there are, I think, 18 countably infinite families of groups, and then there are these 26 exceptions that do not fit that systematic pattern. But what is clear about the 26 exceptions, which are the sporadic groups from where the Mathieu groups are coming from, is that they have got orders that are at least manageable. They have got smaller orders as you compare to the other 16 classes in the classification of finite simple groups. So we felt for us to be able to do more with these groups, we need to work with the sporadic groups because their orders can be handled with computers and so on. And the Mathieu groups are the first class, of the sporadic groups that conveniently we found ourselves bumping into. So M11 is the smallest simple Mathieu group, and then the larger, the bigger one from there is M12, and so on. There are 5 of them. But now this is the thing. When we delve into the Mathieu groups and try to get more information about their structure, the information was not really much. And that is what attracted us to say, yeah, well, we need to know more about this second. Let's allow them to act on some set and see what we get out of that action. So that's how we found ourselves here. So first with M11, we were able to get to publish a paper with that. Then we wanted to be able to compare the structures that we were getting in M11 with M12. We would be a lot of similarities. We were hoping to get similarities so that maybe the work with M12 would be a little simpler. But the reality was that was far from the truth. M12 was behaving completely differently from M11. There are a lot of variations with M12 that were, in fact, it took us more time to work with M12 than we did with M11. So that's how we landed ourselves here. I don't know if that is convincing response enough.
I don't know if I can add something.
Go ahead, Bernardo.
Yes, Dams, thank you. This is a very interesting question.
Yeah.
In the realms of these sporadic groups, the small Mathieu groups have interesting and distinctive features of their own. In the specific case of M11 and M12, and of the Mathieu groups in general, there is a pattern which is, if you notice in the table that Stuart indicated, in the table of maximal subgroups, you will see that M11 is a maximal subgroup of M12 there. And that you will see that the first class, T1, the 2 classes, M11 is there. But that doesn't stop there. The maximal, the sporadic groups of the type Mathieu, they have been constructed as stabilizers of points in an ascending chain in a way that 11 sits in 12, then 12 sits in 22, 22 sits in 23, and 23 sits in 24. And these are the only ones. And the way to study them is by looking at the point stabilizer. And because the point stabilizer is a maximal subgroup, then there is an if and only if relationship between maximality and primitivity to the extent that this brings about the primitive action. And because the maximal subgroups are acting on the blocks, then this is the reason why we are saying it's a block primitive action. Apart from that, there is also geometric knowledge available in regards to M11 and M12. One of purely geometric structure and the other of purely geometric and algebraic. The geometric one is that M11 is the automorphism group of a Steiner triple system. And M12 also has that action. In fact, M11 and M12 are examples of the highly transitive groups. The highly transitive groups having the symmetric group and the alternating group acting highly transitively. And then the Mathieu groups, M11 and M12, are the other cases away from the infinite family of the symmetric groups. That's the geometric connection. The algebraic connection is that this embedding forms a sort of a chain, and we were trying to understand why is this chain proceeding. And these designs have revealed one thing. When you're at M11, you remain at M11, and the largest action that you can have of a group which is not of extension type is symmetric 11. And the reason for that is that the Mathieu group M11 has itself as an automorphism group. In the case of the Mathieu group M12, It is Mathieu group M12 extended by an involution. This involution does not belong to the group, it's an outer involution. So basically it's an M12 extended by 2, as you've seen the revelation in the automorphism groups. Now, this has given us an idea that whenever you have an automorphism group that is larger than the group by some constant or by some element, the behavior of the automorphism group is atypical. And this, to some extent, is why we chose to do it in that way. Adding to that, there is also the notion of the Schur multiplier, which is a homological notion. And we're also interested in finding out what connections can we find. But time is just little, we can't do more than that. We can't look at the homological structures associated to that. Then we stopped only at the algebraic structure. This is, in a nutshell, the motivation for why we chose to do the Mathieu M11 and M12.
Thank you, Gomani. I don't see any further hands from this room, so let us thank Stuart again.
Thank you so much. It has been a pleasure to go through this presentation. Thank you.
Thank you.